Hi, in this video we're going to be finishing our discussion of 14.4, the second half, which is going to talk about the theory of differentials. So differentials is different than derivatives, though related for sure. They'll have some similar notation, but I don't want you thinking we're just talking about derivatives. Would that it were so simple. So in 2D, this is not a topic usually covered in Calc 1 or Calc AB, but it's very, very similar to topics that are. In 2D, we have a tangent line. This will sound exactly like we started last video. We'll have a curve, a point on the curve, and a tangent line through that point, tangent to the curve at that point. So this is my tangent line, this is my function, and this is a point Q, okay? That's the second point Q. So we're gonna have two contrasting topics here. We're gonna have the delta y, which will be called the increment, or the actual change, but the official word is going to be called the increment. And then the dy, which represents the differential. And you should recognize that notation. That would show up in derivatives, that shows up in, the other one, antiderivatives, integrals, all that stuff, okay? In the picture, what's going on? Well, starting from P's height, that's y naught. That's the y we have. And so we're measuring. This is the actual change in y. That's what I mean by the actual change. That's the increment. That's how much the y-coordinate has changed as we progressed along the curve. But you might be thinking, but if we use the tangent line, the difference, if I project the point down to this other point that's below Q, this guy would be called the differential, the dy. All right, so what we're holding fixed here is the change in x, I'll say. If you're wondering how are we going to measure whether they stay the same, that's going to be the change in x, and that is the same on both the tangent line, that is the same on both the tangent line and on the curve, right? That's because it's the independent variable. So the independent variable is not affected by changing which curve we're on. That's what makes it the independent variable. What got affected was the difference between how the y-coordinates changed if we traveled along the tangent line versus how the y-coordinates changed if we traveled along the curve itself. Okay? This is the gap. So let's write about what we were talking about just now. Delta y gives the total change, actual change, total change in height from P to Q. Now that I've written it down, maybe if you're more of a visual learner, a verbal learner, and you have to see the words, you'll see that that's what we're measuring. That's what my gap is supposed to measure. It's measuring the distance in height from P to Q. Sorry. dy gives the change in height from P to a point on the tangent line at x plus delta x, okay? So it's like if P is the coordinates, sorry, x naught plus delta x. If P is the coordinates x naught, y naught, then Q is the coordinates x naught plus delta x, comma, f of that value. Okay. That's all we're talking about. And the whole theory of calculus, or specifically the sections you would have done on tangent line approximation, is that the big idea was that as delta x approaches 0, gets small, dy, that change, approaches delta y, or they become approximately the same, which is also going to 0, right? They're all going to 0, but that's how we're going to estimate. So this is a major field of study from when there were lots of practical applications before computers. Before computers made it relatively easy to estimate what changing numbers exactly would do. Differentials will still give us a good technique for estimating these changes, and as always, it's important to understand where all the math we're doing comes from. The main reason we're interested in studying the differential is because it's usually easier to calculate. So one of the reasons these are easy to calculate is because it's nice. We get a nice formula by abusing the notation here, literally. So if f prime of x is dy dx, then we can solve for dy by multiplying both sides by dx, the differential for x. So it's sort of like the increment of y, which is approximately equal to dy. The increment of y can be estimated by using f prime of x times the differential for x, or the increment of y can be estimated with f prime of x times, since dx is the same as delta x. That's what we're saying. It might remind you of a mean value theorem type of statement, which is that the slope of a secant line, the change in y over the change in x, can be estimated with the derivative, especially on small enough intervals, as long as the function behaves nicely. So, what does all of this have to say about 3D surfaces? I know this might look abstract. Why are we doing this? We already know how to do tangent line. Tangent line was ever that bad. Well, again, there's not just one tangent line anymore. So we'd like to figure out a way to use this with a tangent plane sort of construction. So in 3D, we'll have space. So we'll find ourselves a point, and we'll find ourselves the surface. We'll just try to give a sketch of the surface this point might live on. Now, on that surface, this point has a tangent plane, not quite the tangent line anymore. Now, it's easy to imagine this tangent plane is parallel to the xy plane. For our purposes, that's going to make the drawing a little weirder, so we're just going to go with a red tangent plane that's underneath this curve, but still tangent to that point. Okay, so that's what we're picturing. This is a tangent plane. And in blue, we have some sort of curve. we're still going to have some other point. Let's say Q is over here. Oh, I guess I never labeled P is over here. And we want to estimate how much that changed in terms of its height. Okay? There's very much a measurement in terms of the boxes here. I'll show you what I mean in a second of what's going on here. So we can project these points down and talk about their coordinates in the XY plane. So if this is x plus x, x plus delta x, comma, y plus delta y in the xy plane, so like comma 0, if we're thinking about the 3D coordinates, and p is at x comma y comma 0, then this line right here is the change in y. Okay, that might be hard to visualize, but it is. And this is the change in x. Because again, just to be matters clear, that's the x-axis, that's the y-axis in 3D. So there's the situation. So if I measure a flat parallel to the xy plane, that's why it was really important that the plane is not parallel to the xy plane. If I went parallel to the xy plane, that's how I would start to measure the actual increment. So I'll just make this really clear. Delta z, the increment, is the actual change in height from P to Q. Okay, it's very literally going to be Z Z minus Z naught, that kind of thing. It would be, if you can trace along parallel and everything to these lines, trying to stay parallel to the P plane, this is the gap that we would call the change in the height of Z, right? That's how much the Z coordinate changed. And again, I drew it really large. You could picture it's really small. We're just really zoomed in. You can just say, well, I really messed up the drawing. Obviously, that's true. But that's what we're talking about. That's the change in height. If we kept the Z plane fixed, like this green thing is supposed to be the plane Z equals Z naught, right? Whatever the initial Z coordinate was. And that's how far above that plane we are. That's what delta Z represents. That's what the increment of Z represents. Okay, from the initial x coordinates, from our xy pair to our x plus delta x, y plus delta y pair. Okay, dz sorry, just trying to find the right color. dz maybe is the differential still. This is the change in height from P to a point on the tangent plane above our coordinates. So here's maybe where it looks like it intersects with a tangent plane. Maybe purple was the wrong choice here, but that's what DZ is. And as we get closer and closer and closer, if you can visualize my drawing correctly, DZ is going to approach delta Z, the increment. So I want to make a note here, though, that X and Y are both independent variables. So dx is delta x, and dy, the differential for y, is now delta y. So why'd you do that whole example, Mr. Leven, where you said they were going to be different? Well, because in 2D, they would be different. In 2D, y is dependent on x. But now, in our full 3D vision, we have these things are allowed to roam free. Okay, so what we're going to do is recast this and try to estimate that increment in z by using our tangents and our differentials in 2D land. Here we go. So I'm going to draw that figure one more time. X and a y. X and a y. And a z. And we have a surface in 3D land. And we have, here, I'll change it up, make Q over here. P will still be here. If we want to estimate that change in height in the Z, I can go purely along the X component until I get to the right spot along that surface, and then purely along the Y component along that surface. I can trace the curve purely in the X direction, that's just traveling along the X direction, and then purely along the Y direction. Sorry, that doesn't look like the Y. That would be the Y direction. Right? I'm going until I get to the right coordinate, and then I'm going to follow that curve up until I hit the right Z coordinate. No. Backwards. I'm going to go from my home at P. I'm traveling along the X direction only, parallel to the XZ plane, until I lock in my X coordinate. X coordinate's locked in. Now we're going to travel purely along the parallel to the YZ plane along this surface until my Y, X, and Z coordinates are locked in at Q. So we will measure the change in height over here. We could call that the change in height, the increment with respect to Y. And then we could also measure the change in height from our original spot. And we could call that how much change we had, how much gain in elevation we had with respect to X. And so together, our increment, our gain in elevation, was some gain in the X direction plus some gain we made by climbing purely in the Y direction. Now, the power of this, combined with what we talked about in 2D land, is that each of those red lines are curves, are planar curves. They are only changing in one dimension. So we are able to use a tangent line that's stuck in the same curve and estimate that change in z, the z with respect to x can be approximated with a differential in that direction. And that differential, we call it dzx, would be equal to the slope of that line times the change in x along that line, right? Like this line would be the change in x. And if we're using the slope correctly, we know that we can estimate a change in y by multiplying the slope times a change in x, right? The tangent line slope times a change in x. Similarly, along this curve, oh boy, I really messed up with the tangent line here. It's going to look really bad. The tangent line would be like that. So you can see this is going to be whacked out. And so we could estimate that change in z and with respect to y. It's really, the picture is off here. I'll just fix the picture now. I'm not going to re-edit. Oops, I will make it look nicer than that though. Something like that. Sure. Yeah, now we have a nicer, it's still the same change in z total. And, right, so we can estimate that with a dzy. So similarly, our increment with respect to y can be approximated with a differential with respect to y, which is the same as using our slope notions from before, this. Just to refresh that idea that maybe we were unclear about in the previous two slides, we're using this idea that a slope is a rise over a run. We'll keep it in plain Jane language here, so that if I want to estimate our change in z with respect to x, the run would be dx, and the slope would be f sub x, right? For our y stuff, we'd be talking about fy would equal that change in height with respect to y over dy. I guess these should be approximate before we go to exact. So therefore, overall, our differential with respect to z, our increment with respect to z can be approximated by using fx times the increment, or the differential for x, plus fy times the increment with respect to y. And that's the formula, that's the power, that's the simple linearization of it all. Okay. The change in the elevation here, or the change in that physical quantity that's represented by z, can be estimated by just using the slope with x and the slope with y, along with how much those were changing. Many of the problems will just ask you to come up with a formula for the differential. So, what are we talking about? Find the differential of z equals y e to the x squared minus y squared. So, what we need here, okay, the differential, dz, is our partial derivative with respect to x, dx, plus the partial derivative with respect to y, dy. So what we only need here is to find those partial derivatives. This is one of the instances maybe where if everything else I was doing up until now confused you, this should be pretty approachable. And I'll show you how we use this, but we'll get at least one of these problems under our belt. So you should take a break now and pause the video to do these, get back to Earth. What are the derivatives here? 3, 2, 1. With respect to x, almost everything's a constant. But I do have the chain rule to worry about. So I have y times the derivative of the exponent was 2x e to the x squared minus y squared. Everything stays the same. And we might reorganize that to be 2xy. That's usually how that's written. E to the x squared minus y squared. With respect to y, we have to use the product rule first times the derivative of the second. It's going to be negative 2y e to the x squared minus y squared plus the second times the derivative of the first, or just times 1. So that might be written as negative 2y squared e to the x squared minus y squared plus e to the x squared minus y squared. Sometimes we'll factor that just to have a nice expression, especially if we're going to make a differential where we're going to be multiplying it anyway. And we're going to have parentheses anyway, plus 1. So this is how simple it can be. The differential, I'm just going to plug these formulas in for my partial derivatives. E to the x squared minus y squared times the differential for x plus e to the x squared minus y squared times all this junk times the increment, the differential with respect to y. Sorry, the language is definitely getting to me after all this. Now, this doesn't tell you much, especially if you weren't understanding what these graphs with these surfaces were doing. But what we're going to do is we're going to need to know a point on the curve and what is the size of these differentials, and that will allow me to estimate the changes in the actual elevation. I first want to point out, before we go on to do that, that all of what we were talking about works in more than 2 variables. So just to give you a 4D example, 3 independent variables, if we have w equals x squared e to the y plus y natural log z, we can find, I know students always like this, dw, because of Arthur. Well, I hope you still like it. It was a good show while it lasted. The differential with respect to w is going to be a very similar formula, just one step longer. If I left you, you would figure this out. Derivative with respect to x, differential with respect to x. Derivative with respect to y, differential with respect to y. Derivative with respect to z, differential with respect to z. And now, to be clear, z is an independent variable, so its differential would be the same as its increment. The proof would work out exactly the same way, except we don't have any fancy pictures we can draw. We can't draw a 4D function, but it's the same idea. We're just going to add up all the increments in each of the directions, and we would get the total change. And we can estimate each of those increments by using a tangent line in those directions, by holding the other 2 variables fixed in this case. So go ahead, try to find the partial derivatives, because that's really all you're doing here. That's all there is to it. And pause the video and come back and check. 3, 2, 1. The partial derivative with respect to x is 2x e to the y. With respect to y, it's the hardest one, x squared e to the y plus natural log z. It's the only one with 2. I don't know, maybe z threw you off. The natural log just turns into 1 over z, so we're talking about, well, not w, y over z. And so it really is as easy as reassembling this into 2x e to the y times the differential for x plus this whole thing. That's what I'm saying. It's the hardest one. It's the ugliest one, that's for sure. Times the differential for y times this times the differential for z. Okay? Now, one more thing. What I think this is unclear so far why this would be useful. And it's because I'm not really plugged in anything yet. So what are we picturing for dx and dy and dz? Well, the differential is only useful if dx, dy, and dz are small. So if I was going to add more to the previous slides, these differentials are small would mean that dw is really close to the actual change in w. And that's what would go in for those. If we're picturing those as really small numbers. There are some problems where they don't even tell you what the actual x coordinates were. They just want you to, hey, if we got really close, what would the formulas look like? But let's do one example where we actually end up plugging stuff in, shall we? So, yeah. Last example, everything together. We're first going to find the differential for this 4D function. Now I say it's a 4D function. It only has 3 letters though. Why is it a 4D? Because if we wanted to graph it, we'd have to have an output variable. And we would say find df, the differential for f. Well, the differential for f is just the contribution of each partial derivative times its differential. So again, another chance for you guys all to take some partial derivatives, pause the video, assemble a differential. One chance for yourselves. 3, 2, 1. All right. You got 2 over 2x minus y plus 2z e to the 2xz. Derivative of the exponent is 2z. We got negative 1 over 2x minus y. No y's in the second component, so it just goes to 0. Its differential is 0. And the last one's just going to be 2x e to the 2xz. Okay, not so bad. Putting that all together gives me a differential that looks kind of ugly at times. That's the x component. I took out the negative and moved it in front. The y component and the z component of the differential, 2xz dz. Okay, now remember, the component has all 3 letters. Each component has most of the letters. Not all 3 have all 3, but okay. Being the x component doesn't mean the other letters don't change it, right? The slope was dependent on all 3 letters. What do we mean by the x component? We mean that's what happened when we just kept that variable as a variable and the other 2 as constants. That's a differential. And so a follow-up question could be, approximate the change from 2, 3, 0 to 2.01, 2.97, 0.04. Now again, in the modern day, Would this be super useful? Not really, because I could just plug these three in for these three. Everywhere I see X, replace it with 2.01. Everywhere I see Y, 2.97, etc. And just get a decimal using modern computation. But this comes from a place where that wasn't that doable. So we're just trying to show what's going on here. So notice, we're going from a place where X is 2, Y is 3, Z is 0, and we're changing X by how much? What's the differential for X? That's the same as the increment for X. That got incremented up by 0.01. How about for Y? That got incremented down by 0.03. How about Z? That got incremented up by 0.04. So the signs here really matter. Please be careful with that. And we're just going to plug in everything we see. So the differential, which is how we're going to estimate the actual, the actual change in W, would be approximated by the differential for W at those coordinates. Specifically, 2 over 4 minus 3, which is 1, very nice, plus 2 times 0 times e to the 0. That's all going to be 0, though, because it's multiplying with 0, times the change in X, 0.01. Minus 1 over 4 minus 3, still going to be the denominator, times the change in Y, negative 0.03. Wow, another decimal. Plus 2 times 2 e to the 0, because Z is still 0, times the change in Z, 0.04. And if we estimate that further, we're getting, I think that's 0.02. Yeah. So I'm getting, that one's going to be plus 0.03. And the last one's going to be 0.16, which works out to be 0.21. So the actual change in W is approximately 0.21. Now, you have a question on your homework that asks you what the actual change in W is. To get the actual change in W, again, I would plug in actual. Delta W would be F of 2.01, 2.97, 0.04 minus F of 230. Okay, now what's F of 230? F of 230 is 1. And the only way to get this other value is with the calculator. That's the only way to get it. And when I do that in the calculator, I get 1.223. So the estimate is 0.223. Sorry, the estimate is 0.21 versus the actual change, which is 0.223. It's pretty good. It's pretty good without doing any real hard work with the decimals, right? And that's always been the goal of these linear functions, is they're easier to compute with. And that's kind of the whole point of section 14.4. So I hope that was making sense. Again, if the pictures were confusing to you, I'm sorry. Hopefully the math at least made sense. Hopefully the calculus at least made sense. Anyway, thanks for watching. See you in the next one. Bye.